low mechanical roar moves slowly across an open landscape. Not the quick metallic noise of a small excavator. Not the sharp crack of construction equipment. This sound is deeper, slower, almost rhythmic. Metal teeth bite into the earth. Dozens of them, a massive rotating wheel, nearly 20 meters in diameter, turns steadily in the air. Each bucket scoops several tons of soil at once. The wheel never stops. Above it rises a steel structure as tall as a 30-story building. Long conveyor belts carry crushed earth away continuously. At full operation, the machine can move more than 200,000 tons of material in a single day. Standing nearby, a worker looks almost unreal. From a distance, a person appears smaller than the machine's maintenance ladder. This is the Bucket Wheel Excavator, often described as the largest land vehicle ever built. Some of the biggest models weigh over 13,000 tons. Their booms extend longer than a football field. Their electric motors draw power comparable to a small town. And yet the machine itself moves forward at a walking speed of roughly 10 meters per minute. Slow, relentless, almost indifferent to the scale of the earth beneath it. For decades, this machine has appeared in documentaries, museums, and engineering textbooks as a symbol of industrial capability. Images of bucket wheel excavators often accompany discussions of modern mining, large-scale infrastructure, and the technological power of industrial societies. In the common narrative, the story is simple, as industry demanded more energy, especially coal. Engineers responded by building machines capable of extracting earth on a scale that earlier generations could barely imagine. Hand tools became steam excavators. Steam excavators became electric giants. Productivity increased. Labor became more efficient. Industrial societies gained the energy needed to power factories, cities, and transportation systems. In this story, machines like the Bucket Wheel Excavator represent the natural evolution of engineering, a logical step in the continuous expansion of technological capability. The machine is therefore presented not only as a tool, but as evidence of how human ingenuity steadily overcomes physical limits. Visitors see photographs of these machines towering over landscapes. School textbooks mention their enormous size. Engineering museums display scale models explaining their rotating cutting wheels and conveyor systems. The message is usually clear. Technology grows larger, more powerful, and more efficient. And in doing so, it moves society forward. At first glance, the Bucket Wheel Excavator seems to fit this narrative perfectly. It is difficult to imagine a clearer demonstration of industrial power than a machine capable of removing an entire hillside layer by layer. But when historians and engineers begin looking more closely at the documents surrounding these machines, the story becomes slightly less straightforward. Certain details appear repeatedly in technical reports, operating records, and labor documents. Details that rarely appear in the simplified story of progress. For example, why were some of the largest bucket wheel excavators built at a time when many mining engineers were already questioning their economic efficiency? Why did several mines continue operating machines that consume tens of megawatts of electricity, even during periods of declining coal demand? And why do maintenance logs from some operations describe unexpected structural stresses and mechanical fatigue that rarely appear in popular accounts? None of these questions necessarily contradict the idea that the bucket wheel excavator represents an extraordinary engineering achievement, but they do introduce something else, a small pause in the narrative. Because if this machine truly represents the straightforward story of industrial progress, why do so many of the less convenient details of its history appear only in technical archives, and almost never in the way the story is usually told? At first glance, the bucket wheel excavator seems almost too perfect an example of industrial progress. A single machine replacing hundreds of smaller tools. A rotating wheel continuously cutting through earth. An automated flow of material moving across conveyor belts for kilometers. From a distance, the process looks smooth, almost effortless. The wheel turns, the ground disappears, coal emerges. But when engineers began documenting the daily operation of these machines, the reality was less smooth than the images suggested. One of the first details that appears in operational reports is the sheer energy demand. A large bucket wheel excavator does not run on diesel engines like most construction machines. Instead, it connects directly to the electrical grid. Some of the largest machines require up to 30 megawatts of power during operation. That is roughly the electricity consumption of a small town of several thousand people. Long power cables follow the machine as it slowly moves through the mine. Massive cable drums unwind hundreds of meters of heavy electrical line. Inside the machine, dozens of electric motors run simultaneously. Motors rotate the bucket wheel. Motors drive the conveyor belts. Motors move the entire structure forward. The machine does not simply dig. It operates like a moving industrial plant. And like any industrial plant, it rarely runs without interruption. Maintenance reports from several open-pit coal mines describe a constant cycle of mechanical fatigue. The rotating wheel, sometimes weighing over 100 tons, places enormous stress on the boom structure that holds it. Every time the buckets cut into compacted soil, shock loads travel through the steel frame. Over months of operation, microscopic cracks can begin forming along weld seams. Engineers frequently inspected the boom for signs of metal fatigue. Some maintenance logs describe technicians climbing more than 80 meters above ground level to examine structural joints. Even the conveyor belts presented challenges. A typical bucket wheel excavator moves earth at a rate of 10,000 to 15,000 cubic meters per hour. This continuous flow of material means conveyor belts must operate without stopping. But belts stretching hundreds of meters long can develop misalignment. When that happens, thousands of tons of soil can spill from the system within minutes. Workers sometimes had to shut down the machine entirely just to clear the accumulation. And shutting down a bucket wheel excavator is not simple. The wheel itself can take several minutes to slow to a complete stop. The entire structure, weighing more than 13,000 tons, must be stabilized before technicians approach moving parts. Restarting the system after repairs can require hours of recalibration. These interruptions rarely appear in the simplified story of continuous efficiency, but the technical documents mention them repeatedly. There were also environmental conditions that complicated the operation. In winter, freezing temperatures could turn layers of soil into something closer to stone. Buckets designed to cut through loose overburdens sometimes struck frozen ground with violent force. Operators described the entire boom structure vibrating under sudden resistance. During heavy rain, wet soil could clog the buckets. Instead of falling cleanly onto the conveyor belt, dense clay sometimes stuck inside the metal scoops. Workers then had to manually clear the buildup while the machine remained idle. And then there were the operators themselves. Despite the scale of automation, a bucket wheel excavator still requires a crew. Operators sit in elevated control cabins overlooking the rotating wheel. From this height, sometimes 40 meters above the ground, they monitor excavation depth and machine alignment. Several technicians remain on board during operation. Their job is to listen. That may sound unusual, but many experienced technicians learn to identify problems through changes in sound. A subtle grinding noise from the bucket wheel gearbox, a rhythmic vibration along the conveyor rollers. The machine produces a constant mechanical background noise, a mixture of electric motors, moving belts, and cutting metal. When something inside that system changes, the sound changes with it. Operators often describe the machine almost like a living structure. Not because it was intelligent, but because its behavior had to be interpreted continuously. Even the movement of the excavator across the mine presented complications. Despite its enormous size, the machine moves on multiple tracked undercarriages. Each track must distribute weight across soft ground. If the soil beneath the tracks shifts unevenly, the entire structure can tilt slightly. That tilt may seem small, sometimes less than 2 degrees, but when the boom extends more than 100 meters, even a small angle can create enormous lateral forces. Engineers monitored these angles carefully. In extreme cases, operators had to stop excavation and reposition the entire machine. The process could take several hours. None of these details mean the bucket wheel excavator was ineffective. In many mines, these machines did achieve extraordinary levels of production. Entire hillsides could disappear within months. Coal output increased dramatically. But what begins to appear in the documents is something slightly different from the usual narrative. The machine was not simply a symbol of effortless efficiency. It was a massive, delicate balance of forces: electric power, structural stress, soil resistance, human interpretation. And when all of these elements aligned, the machine worked almost continuously. But when they did not, the operation could become unpredictable. What makes this particularly interesting is not that these challenges existed. Every complex machine has complications. What is interesting is how rarely these details appear in the way the bucket wheel excavator is usually presented. Most images show the machine cutting smoothly through the landscape. Few descriptions mention the constant inspections, the structural stress calculations, or the hours spent clearing clogged buckets. Which raises a subtle question. If the daily operation of these machines involved such a careful balancing of mechanical and environmental conditions, why does the popular story usually describe them as if they were simply unstoppable engines of productivity? And once that question appears, other details in the historical record begin to feel slightly more unusual. Details that make the history of this machine feel a little less tidy than the story we are used to hearing. Once the operational details begin to appear, the story of the bucket wheel excavator starts to feel less like a simple engineering triumph and more like a layered historical narrative. The machine itself is real. Its scale is undeniable. A rotating wheel cutting dozens of cubic meters of earth every minute is not an exaggeration. But the way this machine entered the public imagination followed a much simpler storyline. In many popular documentaries, the bucket wheel excavator appears as the logical endpoint of a long chain of industrial progress: hand labor, steam machinery, electric mining equipment. Then finally, the giant continuous excavator capable of removing entire landscapes. The narrative suggests a smooth technological evolution, each step improving productivity, each machine replacing inefficient human labor, and each innovation naturally leading to the next. However, when historians compare this story with engineering archives and industrial planning documents from the mid-20th century, the sequence becomes less linear. One of the first things that becomes visible is how experimental these machines originally were. Early bucket wheel excavators were not immediately recognized as the inevitable future of mining. In fact, several mining engineers in the 1930s and 1940s expressed skepticism about their practicality. The problem was not the cutting wheel itself. The principle of continuous excavation had already been tested in smaller machines. The concern was scale. Once a machine exceeds 10,000 tons of structural mass, many engineering variables begin to change. Steel beams behave differently under constant dynamic loads. Gear systems operating under hundreds of kilonewtons of torque develop wear patterns that smaller machines never experience. And long conveyor systems introduce alignment problems that multiply across distance. Some early technical papers from German mining engineers described the machines as structurally impressive but operationally uncertain. This hesitation rarely appears in simplified histories. Instead, the development of the bucket wheel excavator is often presented as if engineers simply decided to build a larger and more powerful machine and succeeded immediately. But the engineering report suggests something more cautious. Designs changed repeatedly, boom structures were reinforced, gearboxes were redesigned, and several early models required extensive modification after only a few years of operation. Another element that becomes visible in technical documentation is the gap between theoretical productivity and actual output. Promotional materials frequently emphasize the maximum excavation capacity. Numbers such as 200,000 tons per day became widely repeated, but these figures represented ideal operating conditions: perfect soil consistency, continuous electrical supply, minimal downtime. In real mines, those conditions rarely existed for long periods. Maintenance logs from several lignite mines in Central Europe show that large excavators often operated at significantly lower effective output due to mechanical interruptions and environmental constraints. This does not mean the machines failed. They still moved enormous volumes of earth. But the gap between theoretical and practical performance was larger than many public descriptions suggested. Another simplification concerns labor. Popular narratives often describe machines like the bucket wheel excavator as replacing human labor with automated efficiency. Images of a single operator sitting in a control cabin reinforce this impression. Yet historical workforce records tell a more complex story. Operating a bucket wheel excavator requires an entire system of personnel: control operators, electrical technicians, structural inspectors, conveyor maintenance crews, ground stability monitors. In large mining operations, dozens of workers remained involved in keeping a single excavator functioning. The machine concentrated labor differently, rather than eliminating it entirely. Workers were no longer digging with shovels, but they were continuously maintaining the machine that never truly stopped working. Another point of exaggeration appears in the way the machines are often presented as symbols of environmental mastery. The visual image is powerful. A gigantic rotating wheel cutting into the earth as if reshaping geography itself. But environmental reports from several mining regions describe a different dynamic. Large excavators could remove enormous layers of soil, but they were also extremely dependent on geological conditions. If the soil composition changed suddenly, for example from soft overburden to dense rock layers, excavation speed could drop dramatically. In some cases, entire sections of the mine required different equipment before the bucket wheel excavator could continue operating. So the machine did not simply dominate the landscape. It remained constrained by the same geological realities that earlier miners faced. Perhaps the most interesting omission, however, concerns how few of these machines were ever built. Because in the popular imagination, the bucket wheel excavator sometimes appears as if it were a standard industrial tool, a normal stage in mining technology. But globally, the number of truly massive bucket wheel excavators has always been relatively small. Even during the peak decades of lignite mining expansion in the 1960s and 1970s, only a limited number of mines possessed machines of the largest scale. They were expensive, extremely specialized, and dependent on very specific mining environments, which means the bucket wheel excavator was never the universal solution the simplified story sometimes implies. Instead, it was a highly specialized response to particular geological and economic conditions. Yet photographs of these machines became widely circulated. Engineering exhibitions displayed models, industrial films emphasized their size, and gradually, the machine began to represent something larger than its actual operational role. It became an icon, an image that communicated industrial strength, technological ambition, the power of modern engineering. None of this means the machine itself was misrepresented. The excavator truly is one of the most extraordinary land machines ever constructed, but the way its history is often summarized tends to smooth out the uncertainties that surrounded its development. The engineering doubts, the operational complications, the economic limitations, those details still exist. Preserved in technical archives, maintenance records, and engineering journals. They were never hidden, but they rarely became part of the simplified narrative that reached the public, which raises an interesting possibility. Perhaps the story of the bucket wheel excavator was never only about mining technology. Perhaps it also served another function, a function that becomes easier to see when we begin asking a different question. Not just how the machine worked, but who benefited from presenting it as a symbol of unstoppable industrial progress. Seen from a distance, a bucket wheel excavator is more than a machine. It is a spectacle. The rotating wheel alone can reach 18 to 22 meters in diameter. Each steel bucket attached to the rim can hold 6 to 8 cubic meters of soil. As the wheel turns, the buckets cut into the earth with slow mechanical certainty. Dust rises. Conveyor belts begin moving. Within minutes, a hillside begins to disappear. For anyone standing nearby, the experience is overwhelming. The machine is not simply large. It feels geological, a structure so big that the human body has difficulty understanding its scale. And this visual impact is important because long before most people ever saw a bucket wheel excavator in person, they encountered it through images, photographs, industrial films, engineering exhibitions, government documentaries. In many of these images, the machine appears alone in the landscape, the rotating wheel cutting through the ground, a vast industrial structure dominating the horizon. Sometimes a small worker stands nearby for scale, but the overall message remains the same. This is what modern technology looks like: massive, precise, unstoppable. By the mid-20th century, this visual language had become extremely useful for industrial societies. Not because anyone needed to invent a false story. The machines really existed. They really did move enormous volumes of earth. But their image carried symbolic value far beyond the mines where they operated. During the decades after the Second World War, many countries were competing to demonstrate industrial capacity, steel production, energy generation, large infrastructure, heavy machinery. These were widely seen as indicators of national strength. In this context, machines like the Bucket Wheel Excavator became powerful visual evidence of technological capability. A photograph of a 13,000-ton excavator removing an entire layer of soil communicates something instantly. It suggests scale, organization, engineering sophistication, even if the viewer knows nothing about mining technology. This symbolic value helps explain why images of these machines circulated so widely. Industrial companies used them in promotional materials. Energy ministries included them in public information films. Engineering exhibitions displayed scale models of giant excavators. Visitors could look at the rotating cutting wheel and understand immediately. Modern industry had reached a new level of capability. The machine became a symbol of industrial civilization itself, and symbols have a tendency to simplify complex realities. For example, the bucket wheel excavator is often shown as if it operates independently, a gigantic machine carving through the earth alone. But in reality, the excavator exists within an entire system. High-voltage power lines supplying electricity, kilometers of conveyor belts carrying overburden, separate spreading machines redistributing excavated soil, rail networks transporting coal. Without that surrounding infrastructure, the excavator cannot function. Yet the image of this single giant machine is far easier to communicate than the complexity of the entire system. The same simplification occurs in the narrative of economic benefit. Large excavators did increase the speed of material removal in certain types of mines. That part of the story is accurate. But the machines also required extraordinary investment. Manufacturing a single large bucket wheel excavator could take several years of engineering and fabrication. Thousands of tons of specialized steel, massive gear systems, high-capacity electrical components. Entire factories were sometimes dedicated to producing these machines. Only large mining operations could afford them, and only in geological environments where continuous excavation was practical. In other words, the excavator represented not just technology, but concentrated industrial capital. Yet when the machine appears in public narratives, that economic structure tends to disappear. The story becomes simpler. Technology grows larger. Efficiency improves. Production increases. Progress continues. Another layer of benefit appears in political narratives. Large machines have long served as visual proof of modernization. Governments promoting industrial development often highlighted projects that involved visible mechanical scale. Dams, steel mills, power plants, open-pit mines. A giant excavator cutting through the earth fits easily into this visual vocabulary. It demonstrates control over natural resources. It shows that a society possesses the engineering expertise required to reshape landscapes. And perhaps most importantly, it communicates this message without requiring detailed explanation. Anyone looking at the machine understands immediately that something enormous is happening. The rotating bucket wheel becomes almost theatrical, a mechanical performance of industrial power. This symbolic role helps explain why the machine's image often appears in educational materials as well. Students studying industrialization frequently encounter photographs of large mining equipment. These images are meant to illustrate the scale of modern industry, but the images also quietly reinforce a particular interpretation. That technological growth follows a clear and inevitable trajectory. From small tools to giant machines, from manual labor to automated extraction, from limited productivity to industrial abundance. It is a compelling narrative, and in many ways it contains real elements of truth. But as the earlier sections suggest, the historical record surrounding these machines is more complicated. The engineering process was uncertain, operational performance varied, economic conditions shaped where the machines could actually be used. None of this contradicts the idea that bucket wheel excavators represent extraordinary technical achievements. But it does suggest something important about how technological history is often told. Large machines are visually powerful. They compress complex systems into a single object. They allow entire industrial networks to be represented by one dramatic image. And because of that, the machine itself can gradually become a symbol of progress, even if the historical reality behind it is far more intricate. Which leads to another question. If the symbolic image of the bucket wheel excavator became so influential, what do the less dramatic documents actually show? The maintenance records, the engineering correspondence, the labor statistics. Because when those documents are examined carefully, they reveal details that were always available. Details that rarely contradicted the existence of technological progress, but that often made the story of this machine look far less simple than the version most people learned. If we move away from photographs and promotional descriptions, a different kind of record begins to appear. Not dramatic images, not simplified narratives, but technical documents, maintenance logs, engineering correspondence, labor reports. These documents rarely describe the bucket wheel excavator as a symbol. Instead, they describe it as a machine that must operate every day under very specific conditions. And those descriptions often begin with something very concrete, where, for example, the cutting buckets attached to the wheel experience constant abrasion. Each bucket repeatedly strikes layers of soil, sand, and occasionally fragments of stone. Even hardened steel edges gradually wear down. In some mining operations, the cutting lips of the buckets required replacement after several hundred hours of excavation. Maintenance crews monitored the thickness of these edges carefully. If the steel became too thin, the bucket could crack under impact. Replacing a single bucket on a large excavator was not a small task. Technicians sometimes had to position lifting equipment 20 meters above the ground, remove bolts weighing several kilograms each, and lower damaged parts using cranes mounted on the machine itself. Another recurring issue appears in the gear systems that drive the wheel. The bucket wheel does not rotate freely. It is powered by large electric motors connected through reduction gearboxes. These gear systems must transmit enormous torque. Some technical specifications list torque values exceeding 1 million Newton meters. Under these forces, even small misalignments inside the gear teeth can produce gradual damage. Engineering inspection reports frequently mention pitting on gear surfaces, small cavities forming in the metal after long periods of stress. When these pits grow large enough, vibration begins to increase. If ignored, the gearbox can fail. Repairing such a component is an extensive operation. In several documented cases, sections of the excavator had to be partially dismantled so technicians could access the damaged drive systems. The process could take days or even weeks. Meanwhile, excavation stopped entirely. Electrical systems also appear frequently in the documentation. A large bucket wheel excavator relies on an uninterrupted electrical supply. High-voltage cables feed power into the machine's internal distribution network. Inside the structure, transformers and switchgear manage electricity for dozens of motors. Reports from some mines describe situations where voltage fluctuations caused sudden shutdowns. When that happens, the rotating wheel may still hold several tons of soil in its buckets. Operators must carefully stabilize the system before restarting. Restart procedures sometimes required a sequence lasting more than an hour to ensure that motors and conveyor belts resumed operation in the correct order. Labor records provide another perspective rarely visible in simplified narratives. Although the excavator concentrates mechanical power in a single structure, it does not eliminate the need for human monitoring. Technicians regularly patrol the machine while it operates. They inspect conveyor rollers, check hydraulic lines, listen for abnormal sounds from rotating bearings. In some mines, workers walked along maintenance walkways that stretch across the machine's over 100-meter boom. These inspections could occur while the machine remained active, which meant technicians worked within an environment filled with vibration, noise, and moving machinery. Noise measurements from several excavators recorded sound levels reaching over 100 decibels near the bucket wheel gearbox. Communication between crew members often required radio headsets. Another set of documents focuses on ground stability. Because a bucket wheel excavator moves slowly across the mine surface, engineers constantly evaluate the soil beneath its tracks. The machine's enormous mass must be distributed across multiple crawler units. Even then, the pressure on the ground can exceed several tons per square meter. Geotechnical reports describe cases where saturated soil began shifting under the machine's weight. If the ground subsides unevenly, the excavator's structure can tilt. Operators must then halt excavation and reposition the machine to restore stability. These situations are rarely dramatic enough to appear in documentaries, but they appear regularly in technical reports. Perhaps the most revealing documents are production statistics. Monthly reports from open-pit mines often list both theoretical capacity and actual material removed. The difference between these numbers is rarely explained in popular accounts, yet the reasons are usually visible in the same reports. Maintenance downtime, electrical interruptions, weather conditions, geological obstacles. When all these factors are combined, the effective output of a machine may fall well below the maximum figures often quoted in promotional materials. None of these documents suggest that the bucket wheel excavator was unsuccessful. On the contrary, the machine still enabled levels of excavation that earlier generations of mining equipment could not approach. But what these records reveal is a continuous process of adjustment, inspection, repair, recalibration. Engineering journals from the period often describe the excavator not as a finished technological solution, but as part of an evolving system. Design improvements continued for decades. Gear materials changed. Structural reinforcements were added. Control systems became more sophisticated. In other words, the machine's history was not a single moment of invention. It was a long sequence of modifications responding to the realities of operation, and these realities were never hidden. The documents existed. They were archived by mining companies, engineering institutes, and industrial regulators. Anyone studying the machines carefully could find them. But in the broader cultural story of industrial technology, those details rarely became central. The public narrative usually preferred something simpler: a giant machine, an enormous rotating wheel, a symbol of human engineering power. Meanwhile, the quieter records continued to describe the daily realities of operating that machine. The worn bucket edges, the vibrating gearboxes, the slow adjustments required to keep thousands of tons of steel balanced above unstable ground. And once these documents are read together, they reveal something subtle. The simplified story of technological progress was never entirely false, but it was incomplete, because the documents suggest a history that looks less like a straight line of improvement, and more like a constant process of negotiation between machines, materials, and the environments in which they operate. Which leaves one final question. If we remove the simplified story, the symbolic image of unstoppable industrial progress, what actually remains of the history of this machine? If the familiar story of the bucket wheel excavator is set aside for a moment, what remains is still a remarkable machine. A rotating steel wheel nearly 20 meters wide, dozens of buckets cutting continuously into the earth, a structure weighing more than 13,000 tons slowly advancing across an open pit mine. Few engineering creations demonstrate the physical scale of modern industry as clearly as this one. The machine exists. It works. Entire landscapes have been reshaped by its operation. Coal seams buried beneath layers of soil have been exposed through its steady motion. In that sense, the machine truly is an extraordinary technological achievement. But when the simplified story is removed, the meaning of the machine becomes less certain. Instead of representing a smooth narrative of technological progress, the bucket wheel excavator begins to appear as something more complicated. A machine built through experimentation, modified repeatedly after entering service, dependent on electrical infrastructure, geological conditions, and continuous human monitoring. It is not simply a giant tool operating in isolation. It is part of a much larger system. Power plants generating electricity, steel mills producing structural components, engineers calculating stress tolerances, workers inspecting moving parts while standing dozens of meters above the ground. Even the landscapes where these machines operate are not passive environments. The soil composition determines excavation speed. Moisture levels influence ground stability. Frozen layers of earth can temporarily stop the rotating wheel. Every bucket of soil removed is part of a negotiation between mechanical force and natural resistance. When viewed in this way, the bucket wheel excavator still represents technological capability, but it no longer appears as an effortless symbol of control. Instead, it reveals something about how large industrial systems actually function. They are not perfect. They require constant attention, and they remain dependent on conditions that cannot always be predicted. This does not diminish the achievements of the engineers who designed these machines. On the contrary, it highlights how complex the task really was, designing a structure capable of carrying thousands of tons of steel, supporting a rotating cutting wheel, transmitting enormous mechanical forces, and remaining stable while moving across soft ground required extraordinary technical knowledge. But the documents surrounding the machine also show that technological history rarely follows the simple narrative that later descriptions suggest. Uncertainty, trial and error, unexpected limitations. These elements appear repeatedly in engineering records, yet they often fade from the stories told in museums, textbooks, and documentaries. Those stories tend to emphasize clarity, a clear invention, a clear improvement, a clear step forward in the march of industrial progress. The bucket wheel excavator fits that narrative visually. Its scale alone suggests inevitability, but the deeper historical record suggests something else. Technology does not move forward in perfectly straight lines. It develops through adjustments, compromises, and constraints that remain invisible when the story is simplified, which means the machine we see in photographs, the giant rotating wheel cutting through the earth, is only one part of the history. The quieter parts remain in technical archives, inspection notes, engineering diagrams, production statistics, maintenance schedules. Together they describe a machine that was never simply a symbol. It was a working system embedded in a complex industrial world. And perhaps that is the most interesting conclusion, because once the neat story of technological progress begins to loosen, the bucket wheel excavator no longer looks like the inevitable result of history. It looks like a particular solution created under particular conditions. A machine shaped by geology, economics, engineering knowledge, and political priorities. And if such a powerful and visible technology can carry a history that is far more complicated than the version most people know, then another question quietly emerges. If for so long we accepted such an orderly story of technology, how many other histories are we still repeating simply because they fit better into the narrative of progress?